Mathematicians, I'm so excited. I've been missing you. Um, After this chapter, I'm going to try, and especially today with office hours, but I'm going to have some live camera just because I miss seeing all of your faces, smiling and excited to do stats. In this video, I'm going to go over the Chapter 7 lecture, or Chapter 7 material. I ended up leaving off 7.2 and 7.4 as far as notes are concerned, but it is important just to kind of read over it in the book. Um, you might see some questions come back on the project, but it's nothing that I don't think you can't handle. It's just asked whether or not you think there's a relationship between different variables, but it wasn't anything that I thought we really needed to take a lot of lecture time on. So let's go ahead and start with section 7.1. Bear with me on this one because it is going to be a lot of notes. I'm going to try my best to write on my screen, but let me know if there's anything that you can't read, and I'll try to re-tape that or answer any questions you might have. So in 7.1, we're going to talk about correlation. And if you don't want to watch me write all of this, please note that I do have completed notes posted online as well. You can just follow along there if you want to. But if we're talking about correlation, we're talking about a special relationship. And it's a special relationship between variables. So we're going to be measuring a couple things, and then we want to know, is there a connection between those variables that we're measuring? The most important thing with this chapter in statistics in general is that correlation does not imply causation. So just because we can see a connection between two variables, it doesn't mean that one is causing the change in the other. There just is a relationship there. So it's not a cause and effect relationship. When we're talking about correlation, or we're looking for correlation, the way that we graph that is we graph what is called a scatter plot. Ooh, rough handwriting here. But we graph a scatter plot. And in the scatter plot, we're taking paired sample data. And what that means is we're going to have two types of variables. So before, we might have had a bar graph where we say color of car, or we might have a line graph. And then in the line graph, we're saying, oh, in this year, this was the price. But in a scatter plot, we're actually looking at the change in two variables. So we're going to say, for example, the amount of time spent studying and then the grade that the student gets, for example. There are specific ways to set up scatter plots. So we want to make sure that we have whatever we think could be the explanatory variable. I'm going to abbreviate variable here. So the explanatory is going to be on the horizontal axis. We're going to say whatever we think is explaining the response, that's going to be on our x-axis or on the horizontal. The response variable then would be, here's how it responded to that explanatory variable. So we put the response on the vertical. I tend to remember that because alphabetically, E comes before V and H comes before R. So we can put the explanatory variable on that horizontal axis, response on the vertical. Let me scroll down a little bit here. When we're looking to explain correlation, hopefully this is legible. It should be more legible on the picture of notes that I posted. But if we're looking to explain the correlation, we want to look at the strength. So we're looking for the strength. And it's the strength of the relationship. Remember, it is not cause and effect, so it's just a relationship here. And we tend to express this in what is called a correlation coefficient. And we denote that by the letter R. So we can have a strong or a weak relationship. We can also have a positive or a negative. I'm going to clear this screen just so I have a little bit more room to kind of sketch out our different possibilities as far as types of correlation. In the background, you can probably hear my daughter coming up here right now. Okay, so if we're talking about the strength of the correlation or the type of correlation, we have to make sure that we're talking about strong or weak, and then also mention positive or negative. So I'm going to sketch out a couple different possibilities here. We could have a positive and a negative, and then like I said, we could have a strong or a weak. And I'm going to just sketch this kind of a little sloppily just because we're not looking at actual variables here or actual data. But if we're talking about positive, both of the variables are going to increase together, or they're both going to decrease together. With a negative, one is going to increase and one is going to decrease. So if we're looking at to sketch this for a strong positive, I'll set this up this way. For a strong positive, we're looking at a correlation coefficient roughly between 0.7 and 1. So notice that our correlation coefficient, R, will always be between -1 and 1. If we're looking at a correlation coefficient of 0.7, we're saying, okay, most of our data, we can see that there's a positive relationship here. Most of it lies in this same linear type pattern. So as one variable increases here, our variable also increases here. And I'm just sketching one example where we will work more with it. Just to illustrate what it would look like if we had a correlation coefficient of 1, notice that we are in that straight line. So anytime we have 1, it's everything lies in that perfectly straight line. If it's not a straight line, we can approximate something to be close to 1, but it cannot be 1 unless it is exactly linear. Let's look at a week. So here on our week, we're looking at correlation coefficients between 0 and 0.3. Anything in between that would just be moderate or medium. But if I'm looking at 0 or 0.3, so anything kind of in this range, notice again that I'm working with our positive values. So we can see that there's kind of a line, kind of a pattern. As one increases, the other one increases, not as distinct as it is in our 0.7. So we can see there's kind of a pattern, but it's not close to a straight line. Let's look at negative strong. So here we're looking at an R that's about between -1 or -0.7. Again, if it's negative, we know that we're going to have a straight line. So, or if it's -1, we're going to have a straight line. Notice as 1 is increasing, the other value is decreasing. And just to get a general sketch of the -0.7, again, we can see that there's a pattern. It's still close to a line, but not exact. So the relationship there would be a -0.7. Looking down here at the weak negative, we're looking at R about -0.3 to 0. So just like before, except now we're going in a decreasing fashion. We could also have two other possibilities. So that was talking about strong or weak positive, strong or weak negative. But what if there's none? So if there's no relationship whatsoever, then our R is going to be 0. And we can have two different outcomes here. We can have it where we have a horizontal line, or we can have what is called a nonlinear. So notice in this one, it's increasing, so it almost looks like a positive correlation. And all of a sudden it changes to a decreasing. So there's still a relationship there. Sorry, this would actually be nonlinear. There's still a relationship there, but it's not linear. So there's some sort of pattern. The example I like to give with that one is the amount of time spent studying. So again, this one is none, and this one right here is nonlinear. So amount of time spent studying, the more that we study, the better our grade's gonna be. But if we start studying too much, maybe it's taking away from our sleep, or maybe it's taking away from our eating, or maybe it's just overload, information overload. So maybe we reach a point right here, and after that point, now our grade could decrease. And again, I'm just making up an example here. But we can see that there's a relationship, it's just nonlinear. If R is 0, we've got that horizontal line, or we could also have it where just the dots fall over. Again, if you have a hard time reading this, remember I do have these notes posted, completed under handouts. Let's go to the next page here. So again, I'm skipping 7.2, but please do read over it. 7.2 talks a little bit about causes. So just make sure you read over it, but I'm not going to take the time to lecture over it. In 7.3, we're going to talk about what is called best fit line. So this best fit line is going to be a line that lies closest to the data point in a scatter plot. More than any other line. So we want to say, okay, well, my scatter plot maybe looks like this, and I'm looking for a line that's going to be closest to all of my points. So that's going to be our best fit line. And what we want to do with that best fit line is we want to be able to make predictions. But there are a couple cautions that we have to use. So let's say that we have this data here. We have our best fit line. Well, I can make a prediction about a data value that might be here. We can say, oh, well, the number of hours spent studying could probably give me a grade of about this, right? We're making a good prediction, but we have to be careful. So there are 5 different cautions that we need to keep in mind. The first one is we have to make sure that there's a strong correlation in the data. If there's not a correlation and we're trying to just draw a best fit line in there, we're not gonna get a good prediction because it's not most of the data points that are gonna be closest to that line. It's just gonna be a line against a bunch of points. So we have to make sure that there's a strong correlation. I'm going to say strong R and a lot of data points. Remember, that's the same thing that if we were trying to take a sample, we had a very, very small sample, our sample would not be representative of that population. Same thing here. If we don't have a lot of data points and we're trying to make a prediction, that small set of data is not going to explain the overall population. Another caution, we should not use this best fit line for any data that's outside of what we're already given. So we can make a prediction saying, okay, well, if we have this grade or this amount of time studying, we have this grade, but we don't want to be outside of that given data. Because if we're making an assumption, but we don't actually have any data to support it, it's not going to be a very good prediction. That is also pretty much the same thing as our third caution here. So it should not be used for future data. And that's very, very similar than as number 2. Essentially, it's saying if I have data for the last 10 years, how do I know that something won't happen in the next 10 that makes our data completely different? So we don't want to make any future predictions or anything outside of the data that we have. We only want to be able to speak on the information that we have the data for. So again, to be a little bit repetitive, it can only be from the same sample set. If I'm talking about the number of hours spent studying and the grade that students get, I could have 2 totally different results based on different classes, for example, or based on different subjects. Maybe that holds true for a math class, but doesn't hold true for a history. So we want to make sure that we're using the same sample that our data is from if we're going to make a statement about it. And lastly, it does not apply if the correlation is not significant. So if we do not have, I'm going to say we need a linear relationship. So just like we saw in that nonlinear one before, notice that we can't draw a line that fits this data, because over here we would have this line, and then on this side now we would have this line. So we have to have linear relationship, or we can't make an assumption on our data. I'm going to clear this because I want to talk a little bit about this coefficient of determination. So just like we had, I'm going to leave some of these facts over here. Just like we had R as our correlation coefficient, so it was describing the relationship, we also have what is called the coefficient of determination. So let me get this last little bit erased. So R squared is the coefficient of determination. And what this is doing is this is telling us the proportion. Most of the time we'll see that as a percent. So the proportion of the variation. So we're saying, okay, well, we can see that this percent of the difference, or off of the best fit line, this percent of the variation can be explained by the best fit line. So make sure whenever you're interpreting this, we're saying it's the percent of the variation in some variable. And we wouldn't want to write that in our explanation. It would depend on what the variable is. So in some variable that is accounted for by the best fit line. And to find R squared, it's exactly what it seems like it would be. So we're going to take that value that we had of R before, we're going to square it, or essentially we're going to multiply it by itself. I will go on in the next video to go over some of the answers from the practice problems. Notice that the way I'm laying it out is a little bit differently than the way I would have done it in class. Instead of doing the questions as we go, I'm doing the lecture all at one time, and then I'll go over the answers from the answer key separately. So that way we can take some time to practice those questions without me having to pause the video or go at a speed that's not your speed. The lecture will all be done, and then the problems will be talked about separately. So that's going to end this quote unquote lecture for now. And then the next video, I'll go over all of those practice problems to accompany these notes.